Hi guys, in this video I'm going to talk to you about electrical resistance. And before I go into anything else with electrical resistance, I'm just going to put something up here that I'm sure you'll recognize. V equals IR, this is known as Ohm's law. I'm not going to explain that right now, but we will get back to it and we'll go over what all this means. So resistance, as you could guess from knowing some English, is just the fact that something doesn't want to do something, or that it's hard for you to do something, so something is resisting you. In electrical resistance, what's going on is charges are trying to flow through a material, and the material doesn't really let them through very easily. Some materials let them through less easily, some let them through more easily, but that is electrical resistance. So you've got some charge particle Q, so this could be an electron flowing through a metal, say, or flowing through some other material, or this Q, so it could be an electron or it could be an ion, right? And when a charge flows, we call that current. So where does resistance come from? It comes from something called resistivity. Resistivity. That is a material property. So it'd be something like you'd have a resistivity for gold, say, or a resistivity for carbon, or a resistivity for a certain kind of cytoplasm, for instance. If you're more interested in ions flowing than you are for electrons flowing. So resistivity, and we write resistivity as a Greek letter rho here. So that's my attempt at writing a Greek rho. Resistivity, when you take that together with the geometry of an object, so if you say you have a cylinder of a material like this, you can talk about the resistance of the cylinder. So if you put a wire in here, a wire in here, and you want to get current to flow through this thing, you could talk about the resistivity of the material that this resistor is made out of. This probably looks a little bit familiar. You probably saw things like this. They had some colored bands on the side like that, and you probably dealt with those in your physics class. So resistance comes from this material property, resistivity. Material doesn't want to let charge flow. So what's the exact relationship between resistance and resistivity? So we've got an exact relationship here, and again, this is for a cylinder. So if you have the resistance of this cylinder, say we want to find R for the cylinder, we've got the rho for the material that the cylinder is made out of. In your physics class, this was probably some ground up carbon and some ceramic that you never saw, covered by plastic with a couple of wires sticking out to either end. So the resistance R of the object is the resistivity rho, which is a material property again, times the length of the cylinder, so L there, divided by the cross-sectional area. And this will give you some information about how easy it is to get a current to flow through an object. So let's just take a look. And so surface area here would be A, the cross-sectional area A. So let's take a look at what happens with this and see if it makes sense. So what resistance is a measure of, again, is how hard it is to get a current I to flow from one end to the other. And you might get the sense that if you have something that's longer, it's going to be harder for current to flow through something that's longer than something that's shorter, everything else being equal, right? So it makes sense that when L goes up, the resistance R will also go up. So when it gets longer, the resistance gets higher. What happens if you change this area here, A? So if you change A, say you make another resistor out of the same material, the same length, but you make it a lot bigger. Well, it's going to be easier to get current to flow through there because there are more charges to flow. You remember when you're having a current flow through something, you're just picking up the charge particle from the material, and then it's moving down the material. So you've just got more charges to be able to flow through. You've got more charges to pick up. So if you have A go up, R will go down, because there are more charges to be pushed around inside the material. So that should make some intuitive sense to you. So again, resistivity material property. The resistivity has nothing to do with the specific geometry. You can have a resistivity for gold. You don't have a resistance for gold. You can have a resistance for a piece of gold or resistance for a specific piece of carbon, but you don't have a resistance for a type of material like cytoplasm. Resistance, again, material property, doesn't have anything to do with geometry. So at this point, you might be asking yourself, why does this really matter to me? Why is this really important, other than that the MCAT is going to ask you some questions about it? It is actually important to be able to understand systems like this, because there's one very important system in human and other non-human bodies. So pretty much any animal will have a system like this. And I say pretty much because things like sponges don't have systems like this. But this is an axon, right? Or my attempt at drawing an axon. So you've got a part on the outside like this that is made up of myelin, which no doubt you remember, or I hope you remember. So myelin, and myelin is a fatty substance that doesn't let it is very hard to get a charge to flow through the myelin. But on the inside, you've got this cytoplasm, and here you have your cells. So the axon processes cytoplasm, and in that cytoplasm, you've got a bunch of ions that can flow if you put a voltage across this thing. What our bodies do is, to get a voltage to flow down an axon, they dump a bunch of charge in the form of sodium ions in, and those sodium ions push all the other charges down the axon, or they push other positive charges down, so you get an electrical signal propagating down here, and that is a current. So this resistance thing is an important part of your ability to be able to talk like I'm talking to you now, to be able to make hand gestures, which I'm making but you can't see. You need to be able to get an electrical current to flow down this axon, and the way that you figure out how much current is flowing down, let's say you wanted to know something. Let's say you're in a lab, and for some reason you want to know how much current is going to flow down an axon if you put a given voltage across it like this. So let's say that for some reason you're in a lab and it was important for you to know about the amount of current that'll flow down here. You're going to put a voltage on it, so you're going to put a voltage V across it. You want to know something about the current I. So how are you going to do that? Well, you know V because you can control V, because you're the one putting the voltage across it in this scenario. So how do you figure out what R is? Well, you know, this thing has a length. You cut it out of some animal, maybe some you had some tissue, and you cut this thing out. It also has a cross-sectional area, which you might be able to figure out. So this cross-sectional area A. So, and remember, the A is just the part that's going to conduct. So it's from here to here, not including the myelin. Okay, so you've got an area, you've got a length. Let's say you could go and look up in a book somewhere, or some scientific paper, you could go and look up what rho is for the cytoplasm of an axon. So you go and you look that up. So what you can do is you can just take your value for A, your value for L, plug them in over here. So let's call that A sub L sub AX, A sub AX for axon, right? So you've got these two values. You know the cytoplasm value, so you just got R equals rho for the cyto that you looked up. You've got times this length that you cut out, and you know the cross-sectional area, so you just put that in, throw your numbers in, and you get an answer out. And the unit that this would come out in, you'd have some R, and the units on R are what's called the ohm.